Okay, so last time we had this problem where there was a pin joint connected to the wall, and this triangle was 45, 45, 90. The diagonal was 1 meter, so each of these lengths was 0.7071 meters. And the other contact with the ground was a roller at the midpoint here. And we're trying to calculate all these reactions. And the first thing we did was we isolated the whole body. And we called this force, let's renumber the bodies. So this was 1, 2, and 3. And this was A, B, and C. So someone tell me if look back, was this called RB, I assume? Yeah. Okay. And then the bottom one was just R. And then there was also this force this way of 5,000. And we came up with all those equations, right, last time. Can someone tell me what those first three equations are? Zero 0.3535R. Okay. Okay. So there we are. We have three equations, and our variables are the vector RB, the scalar R, and that's all. So we have 3 and 3. We should be able to solve this. Does that mean we're done with the problem? No. How do you know? How do you know you're not done with the problem? Well, if you tried to, what we're trying to do is find the external loads on each of these members. And if you tried to draw a free body diagram of each of these members, you'd end up with forces in them that are not in our list. So we just don't have enough yet. We could solve this and then have a smaller system of equations when we try to solve the structure. But I think I'm just going to leave this as the first three equations, these as the first three variables, and just keep going on with it. Okay, so let's isolate member 1. There are 2 pins on member 1, at A and at B. At B, what is that pin connected to? What member is that pin connected to? 1. And so that means that that any other member connected to that joint has to be connected to member 1. That doesn't end up really coming into it so much at joints with only 2 members. But in this case, what it does mean is, I guess, the reaction load is acting on member 1, okay? Because that reaction load is acting on the pin. So we have a force here that is the reaction RB plus, what's the other force? Yep. So force on 1 by 2. And then at joint A, what member is the pin connected to? Yep. So here you have the force on 1 by 3. And that's all. Nothing else is touching that pin. This one is one where, like, if I was doing this, I would probably skip doing the table. You can do it if it helps. You can skip it if you don't need it. In this case, you can just see that because if we say make this point A the about point, then the row vector for these forces up here, well, if this is the about point, there's no moment produced by F13. And the moments produced by the forces up here are only produced by the horizontal component, and the moment arm is just the length of this. So it's not very hard to calculate that. But anytime you're using Newton's second law on a rigid body, you can write out that table. And you've seen, you know, the lengths of the tests. I mean, you should have plenty of time to write out the tables anytime you want. So let's write it out.
Where do you get RB from again? Sorry. Because it's not.
RB is the force on the structure by the wall. Okay?
Okay.
It's the force,
Oh, I see.
in other words, it's a force applied to the pin by the wall.
So the half-fractional half-normal force.
Well, in this case, it's a pin joint.
Right. Okay.
And so basically, you can think of it as like the bracket that that pin goes into is applying a horizontal and a vertical component of force to the pin. And the pin's part of member 1. Yep. Okay, so pancake, artists, row, 4, marzipan. Let's put the origin down here. I don't remember where we put it originally. Okay. So the force F13 is at the origin. The about point is the origin. So the row vector is 0. The force is F13x and F13y. And the moment, take that cross product and it's 0. And now the force up at the joint B, I'll first do RB. So the coordinates are 0.7071. The about point is zeros. So the row vector is 0.7071. Force vector is RBX, RBY. And so you get minus 0.7071 RBX. And now think about if you were just trying to eyeball this, think about what moment you'd come up with here. You'd have a horizontal component of RB causing, well, with a moment arm of the length, 0.7071. And that force would be causing a clockwise rotation, so the moment would be negative. And that's what we got by doing all the vector calculations too. And then after that is F12. That's at the same point. So all of these are the same. The force is F12x, F12y, and so you get negative 0.7071 F12x. So Newton's second law says F13x F13y plus RBX RBY plus F12x F12y is equal to zeros. And then the rotational equation says negative 0.7071 RBX minus 0.7071 F12X is equal to 0. And so equation 4 says, let's see, I guess I'll probably do it in order F12 before F13. So I'll say F12X. Oh, we already have our BX, don't we? So RBX plus F12X plus F13X is equal to 0. Equation 5 says RBY plus F12Y plus F13Y is equal to 0. And equation 6 says negative 0.7071 RBX minus 0.7071 F12X is equal to 0. So we have 6 equations, and the variables, we have RB, the scalar R, and now we just added 2 more vectors, F12 and F13. Yep, so we have 1, 2, 3, 4, 5, 6, 7 variables. So we're going to have to do another one. And so for this one, I suppose let's just do member 2.
Based off of the information, how do you know you need another one?
Because we have 6 equations, but we have 7 variables. Each of these vectors is 2 variables. So free body diagram of, well, actually, let's do 3. It's just a little easier to figure out what's going on. The calculations are a little easier. But it doesn't matter which one of these you do. Okay, so there are 2 joints here. There is the joint A and the joint C. What member is the pin A connected to? 1. So the pin is not connected to 3. And actually, in this case, there's no difference is going to appear for either of these. But what it is, the force that we're talking about on member 3 by pin A, well, over here at joint A, is the force on 3 by the pin, on 3 by 1. And over here, the pin's connected to member 2. So we have a force on member 3 by the pin, by member 2. Okay. So here we have the force on 3 by 1. Then we have this upward force R. And then over here, we have the force on 3 by 2.
So we can say the negative of F1C.
Yeah, that's great. So that's something you have to do somewhere in the step for this body. So recognize that we've already, we haven't dealt with F23, so we can just leave this one F32, that's fine. But we have dealt with this one with the subscript switched. We have dealt with F13. So I'm going to just right now switch this over to negative F13. That's by Newton's third law. And so now we can go to the table. I guess I'll keep the origin and the about point still at that same point at joint A. So first, let's do this negative F13. Row vector is 0. The force vector is negative F13x, negative F13y, and the moment is 0. And now we'll go to R. The length of this whole thing is 0.7071, so the coordinates where R is applied are 0, no. The x component is 0.3535. The y component is 0. The about point is still 0. So the row vector is 0.3535, 0. The force vector is 0r. And so the moment is 0.3535 r. Okay, so does it make sense that we got a positive moment for r? Yeah, because our about point is over here. That upward force on r is going to make this rotate counterclockwise around the about point. And so that should be positive. And now go to F32. The location of that is 0.70710. The about point is the origin. So the row vector is 0.70710. The force vector is F32x, F32y. And so the moment is 0.7071 F32y. Okay, so Newton's second law says negative F13x, negative F13y plus 0r plus F32x, F32y is equal to 0. And the rotational says 0.3535r plus 0.7071 F32y is equal to 0. Okay. So what equation are we on? 7? So equation 7 says negative F13x plus F32x is equal to 0. Equation 8 says R minus F13y plus F32y is equal to 0. And equation 9 says 0.3535 r plus 0.7071 F32y is equal to 0. So we have 9 equations, and the variables we have RB, R, F12, F13, and F32. So 2, 3, 5, 7, 9. So now we should be ready to solve it. Okay, so how many rows do we need? 9 rows. Okay, so these are the 9 equations. And then we need 10 columns. And the columns represent RBX, RBY, R, F12X, F12Y, F13X, F13Y, F32X, F32Y, and then the constants. Okay, so can you guys go back to equations 1, 2, and 3 and tell me what we have in those equations? Yeah. One of those, okay.
And then there's a constant that's 35, 45.
And there must be an R also, right?
Not in the first one.
Oh, in the second one, right. Okay, so, and then we have RBY, 1 RBY plus 1 R is equal to 35, 35. And then equation 3.
We have a 0.3535 R. And 2500.
Okay. And now equation 4.
We go to RBX.
Okay.
And then F12X. And then F13X.
Okay.
And then 5, we have an RBY.
Okay.
And we have an F12Y. And an F13Y.
Okay.
Number 6, we have a negative 0.7071 RBX. And then we have a negative 0.7071 F12X.
Okay.
7, we have a negative F13X.
Okay.
A positive F32X. 8, we have a negative F13Y.
Okay.
A positive R. And a positive F32Y.
All right.
And then in the last one, we have a 0.3535 R. A 0.7071 F32Y.
Okay. So I do have answers for these. Why don't you take a minute and plug these into your calculator and compare your answers to what I got?